Ever wondered about the unseen forces that keep our homes, our offices, our very lives safe from electrical hazards? It's not magic, it's meticulous engineering. Imagine a massive, incredibly detailed instruction manual, constantly evolving, that dictates every single wire, every switch, every socket in your world. Well, that's precisely what we're about to explore today. We're taking a deep dive into ASNZS 3000.2007, more commonly known as the Australian-New Zealand Wiring Rules. This isn't just some dry, technical document that sits on a shelf. It is the fundamental blueprint for electrical safety for millions. Our mission today is to pull out the most important, surprising, and truly actionable insights from this comprehensive standard, helping you understand not just what the rules are, but why they are absolutely crucial for preventing everything from a minor shock to devastating fires and costly equipment damage.
And what's remarkable about these rules, I think, is how they truly function as a living document, constantly adapting to breakthroughs in science, new technologies, and evolving electrical systems. It's not a static set of guidelines, frozen in time. It's a dynamic framework that's regularly reviewed, amended, and republished to ensure its ongoing relevance and currency. You'll find yourself genuinely surprised by the sheer level of detail, the foresight, and the collective expertise involved in crafting a standard that has such a direct and profound impact on public safety every single day.
Exactly. We're going to peel back the layers on everything, from the most basic principles of electrical protection to the incredibly specific considerations for, say, installing a power outlet in your bathroom, or even the intricate rules governing a generating system that connects back into the main power grid. So for you, our listener, this means gaining a much deeper appreciation for the robust safety systems that underpin our entire modern electrified world and how that safety is rigorously and continuously maintained.
The foundation: what are wiring rules and why do they matter?
So let's start by unpacking this concept of standards being living documents. You mentioned ASNZS 3000.2007 is a prime example. That phrase, living document, sounds quite profound, but what does it actually mean in the day-to-day reality of electrical safety? How is it not set in stone?
Yeah, it's a critical distinction. It means that standards like ASNZS 3000 aren't written once and then just, forgotten. They are systematically reviewed on a periodic basis, typically every few years, and new editions are published to incorporate the latest advancements in electrical science, emerging technologies, and improved system designs. Take this specific 2007 edition. Between its initial publication and the subsequent major revision, Amendment Number 1 was released in July 2009, and then Amendment Number 2 followed in December 2012. And these weren't minor editorial corrections. These amendments introduced substantial changes, and the document itself marks these changes clearly with a marginal bar and the amendment number next to the affected clause, note, table, or figure. This constant vigilance, this dynamic updating, ensures the rules truly keep pace with innovation and, crucially, with new safety insights gleaned from real-world experience and ongoing research. This leads to a really important question, doesn't it? Why is it so absolutely vital for everyone who uses these standards, especially electrical professionals, to always be using the very latest version, including all its amendments? It's because relying on outdated information can literally lead to dangerous installations. An electrical system that was compliant with an older version might simply not meet the most current, safest practices, putting lives and property at risk.
That makes incredible sense. It's almost like a software update for safety, really. How then do electrical professionals ensure they're always working with the correct, most current version?
Well, the document itself provides clear guidance. It points users directly to resources like the Standards web shop at www.sayglobal.com or the Standards New Zealand website at www.standards.co.nz for the latest updates and detailed information.
Okay, so the info is there. This really underscores the continuous responsibility that falls on electrical professionals to stay absolutely current in their knowledge and practice. It's definitely not a set it and forget it industry.
Precisely. Now let's move on to another foundational principle embedded within the standard: the concept of deemed to comply. This is quite a clever mechanism, actually, designed to streamline safety. What's ingenious here is how the standard establishes the status for its own Part 2. Essentially, it confirms that if an electrical installation meticulously adheres to the detailed prescriptive provisions laid out in Part 2, it is automatically considered to meet the high-level safety conditions that are articulated in Part 1.
Right.
Think of Part 1 as the overarching philosophical principles of electrical safety, and Part 2 as the practical step-by-step guide to achieving those principles. This deemed to comply principle also extends to other related standards, like ASNZS 3018, which deals with simpler domestic electrical applications.
So it's essentially like a shortcut to confidence. By carefully following these detailed practical rules in Part 2, you're automatically fulfilling the broader, fundamental safety requirements outlined in Part 1. It simplifies the compliance process for installers, providing a clear, actionable pathway while rigorously maintaining the necessary safety levels without having to reevaluate fundamental principles on every single job. It sounds incredibly efficient.
It is, and it removes ambiguity. And while we're discussing the document itself, a point that often goes unnoticed but is quite significant is the intellectual property aspect. The copyright for ASNZS 3000.2007 is explicitly retained by Standards New Zealand, or SNZ. While it might seem like a small administrative detail to the casual observer, it truly highlights the immense intellectual property, the rigorous research, and the collaborative effort that goes into developing these absolutely critical safety guidelines. These aren't simply public domain suggestions, they are meticulously crafted authoritative documents.
And the source material is remarkably strict about how this copyrighted material can be used. It explicitly states that authorized users will undertake not to copy, modify, merge with other software or documents, or circulate electronically without securing the prior written permission of SNZ. Furthermore, a document, whether it's an electronic or hard copy form, under no circumstance may be sold or transferred to a third party. And it goes even further, stating it, under no circumstances may be placed on a network of any sort without express permission. That's a significant level of control.
It really is. The broader implication here is that these stringent restrictions aren't just about protecting revenue or intellectual property in a commercial sense. They are fundamentally about ensuring the absolute integrity and unwavering control over the authoritative source of electrical safety information. This prevents unauthorized, potentially modified, or even worse, outdated versions of the standard from circulating. Imagine the chaos and the potential danger if an electrical contractor or a building inspector based their work on a slightly altered or outdated version of the rules.
Yeah, that would be bad.
It could lead to confusion, non-compliance, and critically unsafe installations. By maintaining such strict control over the master document, Standards New Zealand ensures that everyone involved in electrical work is literally operating from the same, most up-to-date and verified safety blueprint. It's a proactive measure against accidental or deliberate safety compromises.
Core safety principles, guarding against danger.
Okay, let's dive into what is arguably the most fundamental principle of electrical safety: protection against electric shock. The standard is absolutely crystal clear here. It demands that protection shall be provided against shock current arising from contact with parts that are live in normal service, direct contact, or parts that become live under fault conditions, indirect contact. This really caught my eye. Most people just think of exposed wires, but this immediately tells you there are two insidious ways electricity can harm you, and the standard addresses both head-on.
That's the crucial insight. It's about designing layers of defense. So, direct contact refers to touching an exposed live part that is intended to be live under normal operating conditions. Think of the exposed terminals inside a junction box, for instance. Indirect contact, on the other hand, is touching a conductive part, like the metal casing of an appliance or a switchboard that is not supposed to be live, but becomes energized due to an electrical fault, perhaps a frayed wire touching the casing. The takeaway here is that safety isn't just about what you see, it's about protecting against hidden dangers that emerge when something goes wrong. Live parts must be inaccessible, and any accessible conductive parts must never become live, either normally or in a single fault scenario.
The document specifies various methods to achieve this protection. One is protection by obstacles. Though the standard wisely notes these are only for preventing unintentional contact, they won't stop someone determined to circumvent them. Another widely used method is protection by placing out of reach.
Right, the out-of-reach method sounds straightforward, but it comes with precise conditions. It's typically restricted to installations where access is limited to competent persons, someone qualified and trained, or those under the supervision of competent persons. You wouldn't apply this in a general public area, and here's where it gets quite specific. Simultaneously accessible parts at different voltages shall not be within arm's reach. To give that a tangible dimension, the standard defines within arm's reach as not more than 2.5 meters apart.
2.5 meters.
Yes, so if you can stretch out and touch two different voltage points, and they're closer than 2.5 meters, that's considered a hazardous simultaneously accessible situation, and it's explicitly prohibited under this protection method. It's about preventing that single point of contact, creating a complete circuit through a person.
Beyond just obstacles and placing things out of reach, what other fundamental methods does the standard specify to prevent shock? I see it mentions preventing fault current passage using something called Class 2 equipment, which I understand is equipment with double insulation. It also talks about electrical separation of the system or limiting fault current to below shock values. But the most common and arguably the most crucial method it highlights is automatic disconnection of supply.
Automatic disconnection of supply is indeed the cornerstone of modern electrical safety. This refers to the rapid tripping of a protective device, like a circuit breaker or fuse, almost instantaneously when an electrical fault occurs. It quickly cuts off the power to the faulty circuit, thereby preventing prolonged exposure to dangerous voltages. And yes, Class 2 equipment with its double insulation provides an additional inherent layer of protection, making it less reliant on the building's earthing system for safety.
So it's not just about guarding against direct contact with live wires or faulty casings. Protection is also needed against the harmful effects of abnormal voltages throughout the system. What are the common sources of these abnormal voltages that the standard is concerned about?
That's a great distinction. While power surges from lightning or grid fluctuations are one type of abnormal voltage, the standard is thinking about any unintended voltage that could harm you or your equipment. This could arise from a fault between live parts of circuits supplied at different voltages that are not meant to interact, or perhaps voltages induced into unused conductors from adjacent live ones, a phenomenon known as electromagnetic induction. It could also stem from any harmful influence, perhaps electrical interference, between different circuits or installations. This highlights the complex interplay of electrical systems and how external factors can also introduce hazards. The standard even cross-references other relevant standards, like ASHA 009 for telecommunication cables near high voltage lines and AS&ZS 3080 for general electrical interference, showing just how interconnected these safety considerations are across different utility types. It's about maintaining the purity and stability of the electrical supply.
Okay, so beyond a sudden fault, what happens when simply too much current flows through a circuit? That's where overcurrent protection comes in, safeguarding against both overload and short circuit currents.
Exactly. This is where we delve into the core engineering of circuit protection, and a fundamental condition comes into play, often referred to as the IBEARN-IZ rule. Let me break that down in a practical way. Imagine it like managing the flow of water through a pipe. IB is your design current. That's how much current you intend to flow through the wire based on your appliances. IN is the nominal current of your protective device, like a circuit breaker. That's the maximum amount of current your breaker is rated to let through before it shuts off. And IZ is the continuous current carrying capacity of your cable. That's the absolute maximum amount of current your cable can safely handle without overheating.
Right, okay.
The rule demands that your design current must be less than or equal to your protective device's rating, which in turn must be less than or equal to your cable's capacity. For specialized protective devices like high rupturing capacity or HRC, fuses which are built to handle truly explosive amounts of fault energy, the rule is even stricter. The nominal current of the fuse must not exceed 90% of the cable's capacity. The broader implication here is that this precise coordination ensures that your protective device always trips and cuts power before your cable overheats, melts its insulation, and potentially starts a fire. It's a critical, almost invisible layer of fire prevention.
So the goal is always for the fuse or circuit breaker to be the weakest link, ensuring it sacrifices itself to save the cable. The standard also discusses coordination of overload and short-circuit protective devices. It notes that in some cases, one device can actually provide both protections if its breaking capacity, its ability to interrupt a fault, is sufficient.
That's spot on. But if separate devices are employed for overload and short-circuit protection, then their characteristics must be meticulously coordinated. The critical requirement is that the energy let through by the short-circuit protected device does not exceed that which can be withstood without damage by the overload protected device. End quote. This is complex engineering for critical safety. It means the short-circuit device, which handles sudden, massive surges, has to act incredibly fast, literally within milliseconds, to protect the slower overload device from being destroyed by that surge of energy. The standard even provides a detailed formula for calculating the maximum RSU fault clearing time within switchboards to minimize damage, taking into account variables like the prospective fault current and the switchboard's current rating. This is a deeply nuanced detail, aimed at preventing catastrophic failures in high-power distribution points.
Speaking of high currents, the standard has very specific rules for switchboards serving what it defines as heavy current circuits. That's a substantial 800 amperes or more per phase. What's the primary concern here?
For these heavy current circuits, the primary concern is the prevention of arcing faults, which are incredibly destructive and generate immense heat. The standard mandates that the supply conductors leading up to the protective device in the switchboard shall be provided with means to reduce the probability of initiation of arcing faults by insulation or by separation. This translates into strict internal separation requirements within the switchboard. We're talking about physically separating bus bars from functional units from each other, terminals from the bus bar, and even ensuring safety service circuits are kept entirely separate from general installation circuits. This level of meticulous internal separation is absolutely crucial for high-power installations. It's like compartmentalizing risk within the electrical heart of a building, ensuring that a fault in one section doesn't cascade into a catastrophic failure across the entire board. It's a key engineering principle for fire and explosion prevention.
Now, let's talk about something most homeowners have probably heard of: RCDs, or residual current devices. You often see them advertised as lifesavers. But here's a surprising nuance from the standard. It explicitly states they are not a primary safety measure. That really makes you stop and think.
It's a crucial distinction, and one that's often misunderstood, I find. The standard is very clear. RCDs with a rated operating residual current, not exceeding 30 MAA, are designed for additional protection. They are to be used where excessive earth leakage current could present a significant risk of electric shock. They augment other protective measures, they don't replace them entirely. This raises an important question, right? Why aren't they considered the sole means of protection?
Yeah, why not?
The simple answer is that RCDs are specifically designed to detect and respond to earth leakage faults, current flowing where it shouldn't, to earth. They don't protect against faults that occur directly between live conductors, nor do they protect against dangerous voltages that might be imported into the earthing system through the supply system's neutral conductor. So, while incredibly effective for their specific purpose, they are part of a layered defense, not the entire defense.
Okay, so where are these RCDs specifically mandated, given their additional role? For residential electrical installations, this additional protection by 30 mA RCDs shall be provided for final subcircuits supplying A, one or more socket outlets, and B, lighting points. They're pretty much everywhere you might plug something in or switch on a light at home. They are also frequently required by occupational health and safety legislation in workplaces, underscoring their importance in environments where people are regularly interacting with electrical equipment.
And what's a very smart design recommendation of the standard is to have separate RCDs for different circuits to minimize the impact of the operation of a single RCD. This is a user convenience feature built on a safety foundation. Think about it. If one RCD trips due to a minor fault in, say, your garage circuit, your entire house doesn't go dark.
Right, just that one circuit goes off.
Exactly. Only that specific circuit is isolated, allowing you to quickly identify and address the issue without disrupting all your lights and appliances. It's about combining safety with practical resilience.
The components, wires, cables, and equipment.
Let's transition from the protected devices to the very veins and arteries of any electrical installation, the wires and cables themselves. How are these absolutely vital components selected and installed according to these comprehensive rules?
Well, the standard dictates that wiring systems shall be selected and installed so as to effectively protect against the presence and extent of relevant environmental and other influences. This is a surprisingly broad and critical requirement, actually, encompassing a whole array of challenges. We're talking about protection against mechanical damage, the corrosive effects of weather and water, the subtle but persistent damage from flora and fauna, pests chewing cables, the unpredictable forces of seismic activity, the insidious creep of excessive dampness, corrosive fumes that can degrade materials, the accumulation of dust which can lead to overheating or tracking, the pervasive presence of steam, oil, extreme temperatures, explosive atmospheres, and even constant vibration. This truly showcases the incredible robustness and foresight required in selecting and installing cables to ensure long-term safety and reliability in incredibly diverse conditions, from a dusty farm shed to a high-rise office.
The standard even gets into the granular specifics with tables like cable types and their application in wiring systems and limiting temperatures for insulated cables. It specifically states that polymeric cables with normal use temperatures below 75 degrees C are deemed not suitable for Australian or New Zealand conditions. That's a clear climatic consideration right there.
It absolutely is, and it's a practical note for our local conditions. For instance, the standard highlights that V90 and V90HT insulated cables are designed to operate at higher temperatures 90 degrees C and 105 degrees respectively. This allows them to be used in challenging high ambient temperature locations, such as within the confined spaces of equipment wiring or in hot ceiling cavities, provided they are adequately protected against severe mechanical damage. Without such robust cable types, installations in hot climates or high-temperature environments would face accelerated degradation, leading to safety issues down the line.
So it's not just about the type of insulation. Size clearly matters, especially for electrical conductors. The nominal minimum cross-sectional area of conductors sets important baseline requirements, ensuring wires are thick enough for the job.
And it gets particularly specific about the neutral conductor, which is often overlooked but critical in multi-phase systems. The standard mandates that its current carrying capacity in multi-phase consumer mains and submains shall be not less than that of the largest associated active conductor. This ensures it can handle potential current imbalances. However, there's a fascinating engineering exception. A smaller neutral is permitted if the predominant load consists of multi-phase equipment and the neutral capacity is still not less than the maximum out-of-balance current, including harmonics. This accounts for more complex load profiles where nonlinear loads can generate problematic harmonic currents in the neutral.
Harmonics, right?
And for combined protective earthing and neutral, or PEN, conductors, which serve both safety and current carrying functions, there are specific size requirements to ensure both functions are adequately served, particularly to ensure the earth fault path is always robust.
It's not just about physically getting power from one point to another, but ensuring the voltage remains stable enough. The standard requires that voltage at the terminals of any power-consuming electrical equipment shall be not less than the lower limit specified in the relevant electrical equipment standard. This is crucial for performance, right? There's even a simplified method for calculating voltage drop, which allows you to add percentages across different circuit sections.
Absolutely. Think of it like water pressure. If the voltage drops too much, your lights dim, your motors overheat, and your appliances might not function correctly or even get damaged over time. The simplified voltage drop calculation is a really practical tool for electricians. Instead of complex formulas, they can just add percentages for each section of a circuit to ensure the cumulative drop doesn't exceed the safe limits. This is critical for ensuring reliable and efficient operation of all connected equipment and preventing premature failure. It's a balance between cable cost and system performance.
When it comes to connections, what are the rules around cable joints? They must be enclosed, example, in a junction box to provide adequate protection against relevant external influences. But what's interesting is that some joints are explicitly prohibited when the cable is in tension, like parallel web, neutral screened, or multi-core cables. Why not ban that?
That ban is a direct safety measure against mechanical failure. When a cable is under tension, even a well-made joint becomes a point of weakness. Those specific cable types have internal structures that could be compromised under stress at a joint, leading to a dangerous open circuit, or worse, an exposed live conductor. It's a very practical rule to prevent failure from mechanical stress over time. And a universal visual cue for safety that's truly fascinating is the precise identification of conductors by color, specified in Table 3.4. For instance, the standard unequivocally states that conductors with green-yellow or green-yellow combination colored insulation or sheathing shall not be used as active or neutral conductors.
Ah, the green and yellow earth wire.
Exactly. It's an almost universal visual language. You instantly know a green and yellow striped wire is for earthing, no matter the context. The standard even addresses the coordination of these colors with European practices, highlighting the international alignment of these critical safety standards.
Beyond the selection and internal makeup, how are these cables physically installed? I imagine support is key. The standard mandates that wiring systems shall be supported at suitable intervals to prevent the undue sagging of cables. This includes cables run along walls, ceilings, and roofs. It seems obvious, but what are the risks of unsupported cables?
Sagging cables don't just look untidy, they're a significant safety hazard. They can pull free from terminals, creating exposed live conductors. They can also be snagged, accumulate dust and debris, or be subject to increased mechanical stress, leading to insulation breakdown and potential short circuits or fires over time. Proper support ensures the cable integrity is maintained throughout its lifespan, and a critical rule for concealed wiring, which affects almost every modern home. Wiring systems hidden within 50 millimeters of a surface, be it a wall, floor, ceiling, or roof, and more than 150 millimeters from internal corners shall be protected by one of the methods outlined in Clause 3.9.4.4.
Okay, the 50 millimeter and 150 millimeter rule.
Yes, this rule is designed to prevent accidental damage from someone drilling or nailing into hidden wires during renovations or hanging a picture. A critical consideration then becomes why these specific measurements. It's about defining the most common zones where accidental penetration is likely to occur, typically by someone unknowingly drilling into a wall cavity. It's a proactive measure against common DIY hazards.
And another vital aspect for comprehensive safety is segregation. The standard explicitly states that electrical installations must be separated from non-electrical installations, such as gas and water lines. They also need to be segregated from telecommunications and data cables. What's the thinking behind this?
This is all about preventing compound hazards. If electrical and non-electric services are too close, a fault in one system could easily affect the other. For instance, a gas leak ignited by an electrical spark, or a water leak damaging electrical conduits. Similarly, segregating electrical cables from telecommunications and data tables prevents electrical interference from degrading data signals, and it also minimizes the risk of dangerous voltages being accidentally transferred onto low-voltage data networks in the event of an electrical fault. It's about maintaining discrete, safe operating environments for each utility. And here's where it gets truly interesting for building and fire safety. Is electrical equipment, including switches and socket outlets, is installed in what's defined as a fire-rated barrier, like a fire-rated wall, floor, or ceiling. It must be at least 300 millimeters horizontally and 600 millimeters vertically from any opening or recess in the opposite side of a wall, ceiling, or floor that is required to be fire-rated.
Wow, that's very specific spacing.
It is, and any gaps between the equipment and the barrier must be meticulously sealed to maintain fire resistance rating. This is a critical detail for building integrity, ensuring that fire compartments remain effective and prevent the rapid spread of fire through penetrations. It's the difference between a contained incident and a devastating blaze.
So beyond just the wires themselves, the electrical equipment, the functional components we interact with daily, also have very strict rules. All electrical equipment must function properly under external influences, prevent any adverse effects on the electrical installation, and operate safely when properly assembled, installed, and connected to supply. That's a broad umbrella.
It covers a lot of ground, from resistance to temperature extremes and humidity to ensuring it doesn't cause harmful electromagnetic interference to other sensitive equipment. And critically, equipment enclosures themselves have stringent rules. They must be able to withstand the temperatures produced by the equipment itself, and the standard is very direct. Flammable or readily combustible materials shall not be used for their construction. The standard even points to AS 60529 for the IP, or Ingress Protection, Classification, and Marking System.
Ah, IP ratings, like IP65 or something.
Exactly. This system specifies a precise degree of protection against the intrusion of solid objects in water. This is a crucial practical detail for ensuring equipment suitability for its specific environment, whether it's indoors, outdoors, or in a dusty industrial workshop. It's how you know a light fitting is safe for your bathroom or an outdoor power outlet can withstand the elements.
Let's focus on our everyday power points, or socket outlets. They have surprisingly detailed rules. Socket outlets shall not be installed where the withdrawal of a plug is restricted by a permanent fixture or fitting. I imagine that's to prevent people from yanking on the cord to get the plug out. And they also must be protected from undue mechanical stress or damage.
Exactly. The rule about restricted withdrawal is precisely to prevent people from pulling on the cable rather than the plug itself, which can damage the cable, the plug, or even the socket, creating a fire or shock hazard. The protection against mechanical stress ensures their longevity and safety in normal use. And a fundamental safety requirement is that every socket outlet shall be provided with an earthing contact, with specific exceptions only for systems designed for inherently low voltage, like self-PEL systems. What's particularly interesting is the mandate that each socket outlet shall be individually controlled by a separate switch that operates in all active conductors.
The little switch next to the socket.
That's the one. This switch must be as close as practicable to the socket outlet and clearly marked, unless its control is immediately obvious. This ensures clear and immediate control over the power supply to that specific outlet, a simple but effective safety feature, allowing you to easily isolate power when plugging or unplugging, or when a child might be playing nearby.
To prevent dangerous misconnections, the standard mandates consistent polarization for those common 3-pin flat-pin plugs. Earth, active, neutral in a clockwise direction when viewed from the front of the socket outlet. This seems like a small detail, but it's a fundamental safety consistency, isn't it?
It is absolutely fundamental. It ensures that the live, neutral, and earth connections are always in the expected positions, regardless of how you orient the plug in the socket. This consistency is vital for proper circuit operation and, more importantly, for the correct functioning of safety devices like RCDs, and for ensuring that the earth path is always connected first. It eliminates a common source of wiring errors that could lead to dangerous situations.
Even our lights, something we rarely think about in terms of complex rules, are governed. Lamp holders, for instance, must be protected against damage and minimize the risk of direct contact with live parts when the lamp is removed.
That's a direct protective measure, anticipating user interaction. You don't want to accidentally touch a live terminal while changing a bulb. And more broadly, lamps and luminaires shall be so installed as not to cause undue temperature rise, ignition, or deterioration of the materials they are mounted on or illuminate. They must be suitable for external temperatures and, crucially, installed precisely according to the manufacturer's instructions. This is paramount for preventing fires, especially with modern, powerful lighting. One might wonder about the increasingly popular recessed downlights, those lights flush with your ceiling.
Yeah, lots of people have those now.
The standard has specific requirements here. It mandates specific clearances from building elements or strict adherence to manufacturer instructions to ensure adequate cooling air circulation, especially when they are installed near thermal insulation in a ceiling cavity. Without specific manufacturer instructions, default clearances apply, and a fixed guard of rigid fire-resistant material may even be required to prevent insulation from touching hot parts. This is a real-world safety concern for many homes, highlighting the hidden risks of seemingly simple installations if not done correctly. Poorly installed downlights are a surprisingly common source of house fires.
Good to know. Shifting to heating equipment, like underfloor heating cables, they shall be so installed that they, A, are not in contact with flammable materials, and B, were designed to be embedded, are completely and adequately embedded in the substance they are intended to heat. This directly prevents fire risks.
It's about thermal management. The heat generated by these cables must be dissipated safely into the intended medium, like concrete or screed. If they touch flammable materials like timber or insulation directly, or are not properly embedded, hotspots can form, leading to ignition. It's a very clear fire prevention measure. And electrical converters, like uninterruptible power supply or UPS systems, also have specific rules for circuit protection, requiring individual protection for their submains and final subcircuits. Crucially, they must be arranged to ensure that the continuity of the neutral conductor to the load is not interrupted during bypass or maintenance switching. This is vital for maintaining power to critical loads without dangerous fluctuations or unintended disconnections that could damage sensitive equipment.
And for motors, where unexpected restarting of a motor might cause danger, the standard mandates that means must be provided to prevent automatic restarting after stopping. This prevents dangerous surprises, particularly in industrial or workshop settings where machinery might unexpectedly spring back to life after a power dip.
Exactly. Imagine a large saw or a press restarting on its own that's a severe hazard. This rule is about ensuring operator safety. And even seemingly minor components like capacitors have specific connection rules, often requiring permanent discharge paths to prevent them from holding a dangerous charge long after power is removed. For very large electrical equipment with liquid dielectrics, such as massive transformers exceeding 50 liters of fluid with a flash point not exceeding 250 degrees C, the standard requires stringent precautions. These include fire-resisting dikes or bunds to contain any spills and prevent the spread of fire. This is very specific safety engineering, focusing on preventing large-scale incidents like substation fires.
Earthing the safety net.
Okay, if we think of electrical protection as a complex safety system, then earthing is truly the ultimate safety net. What's its fundamental purpose, and why is it so critical according to the standard?
Earthing is absolutely fundamental for protection against electric shock. Its core purpose is to provide a safe, low-resistance path for fault currents to dissipate to the general mass of Earth. This achieves two critical things. First, it rapidly operates protective devices like circuit breakers and fuses, cutting off the power to the fault. Second, it ensures that any exposed conductive parts that become live due to a fault remain at a safe potential relative to the Earth, so if you touch them, you don't receive a dangerous shock. The standard goes into immense detail about various types of earthing conductors, their precise sizing, and meticulous installation methods. It's the hidden hero of electrical safety.
What are earthing conductors typically made of? I know copper is common, but the standard mentions aluminum conductors may be used as earthing conductors under strict conditions. This includes being solid for smaller sizes, 10 millimeters or less, a minimum of 16 millimeter merge for main conductors, and crucially, not being installed underground or in dam situations. That's a very specific set of limitations for aluminum. What's the reason behind these restrictions?
That's a critical detail, and it's primarily due to aluminum's susceptibility to corrosion, especially in the presence of moisture, and the challenges in ensuring satisfactory long-term electrical terminations. Aluminum can oxidize quickly, creating a high-resistance layer that compromises the integrity of the earth path, making it less effective in a fault situation. In damp or underground conditions, this corrosive effect is significantly accelerated. So, while aluminum is cheaper and lighter, these limitations ensure that its use doesn't inadvertently create a dangerous, unreliable earth path. Copper, being more stable and less prone to such issues, remains the preferred choice for underground or damp applications.
And the cross-sectional area of a protective earthing conductor shall ensure protection against electric shock and provide a path for earth fault current. Its size, the standard explains, is typically determined from Table 5.1 based on the largest active conductor supplying that part of the installation.
Yes, this ensures that the earthing path is robust enough to safely carry the full force of any potential fault current for the time it takes the protective device to trip. It prevents the earthing conductor itself from overheating or melting during a fault, which would leave the system unsafe. Now, where do you physically install an earth electrode, the connection point to the earth? The standard is very practical here.
Yeah.
It shall be installed in a location that satisfies the following conditions.
Mm-hmm.
A, the electrode maintains effective contact with moist soil. B, the electrode is separated from conductive enclosures of other buried surfaces, such as water, gas, telecommunications, and flammable liquid, in order to reduce possible electrolytic action.
Electrolysis.
Right,
Yeah.
exactly. This is a profoundly important site-specific requirement. If the soil is too dry, the electrode won't dissipate fault currents effectively. And if it's too close to other buried metallic surfaces, it can accelerate corrosion in those surfaces due to electrolysis, potentially leading to dangerous leaks in gas or water pipes. It's about maintaining both electrical safety and the integrity of other vital infrastructure.
Now, this concept sounds a bit technical. Equipotential bonding, what does it actually mean? And more importantly, why should our listeners care?
It's one of the most critical yet least understood aspects of earthing safety, I think. Equipotential bonding is about preventing dangerous voltage differences between simultaneously accessible conductive parts. If we connect this to the bigger picture, it ensures that if an electrical fault occurs and one conductive part accidentally becomes live, say a metal pipe or a concrete slab with rebar, then all other accessible conductive parts in that area rise to the same electrical potential. This means there's no voltage difference between them, and therefore, if a person touches both simultaneously, no dangerous current can flow through their body. It literally bonds everything to the same electrical potential, making it safe to touch. It's like creating a giant, perfectly level safety platform.
That's a powerful image. So where is this equipotential bonding most critical? The standard specifies it's crucial in specific locations like showers and bathrooms, where any conductive reinforcing within a concrete floor or wall shall be bonded to the earthing system. And it's absolutely critical for swimming pools and spas, extending to conductive pool structures, and extraneous conductive parts like metallic pool ladders. This directly impacts the safety of recreational areas where water and human contact dramatically increase the risk.
Those are prime examples because of the inherent increased risk when water is involved, or when a person is likely to be wet or immersed, making them more conductive. The standard also specifies that the selection and installation of equipotential bonding conductors follow rules similar to protective earthing conductors, with specific size determinations from Clause 5.6.3.2. This consistency ensures the integrity of the entire earthing and bonding system, creating a cohesive safety network.
How fast does the power actually need to be cut off in the event of an electrical fault? The standard specifies incredibly strict disconnection times.
Time is absolutely critical in preventing serious injury or fatality from electric shock. For a typical 230V supply, the maximum disconnection time is a mere 0.4 seconds for final subcircuits that supply socket outlets having rated currents not exceeding 63 amperes, or to handheld Class I equipment, or 3, portable equipment intended for manual movement during use.
0.4 seconds, that's fast.
Incredibly fast. For other, less immediate risk circuits, like those supplying fixed appliances, it's 5 seconds, provided people aren't exposed to unsafe touch voltages. This raises a crucial question. Why such a stark difference in disconnection times?
Yeah, why the difference?
It's because of the much higher immediate risk associated with portable and handheld equipment. If you're holding a faulty power tool, you need the power cut instantly. zero point 0.4 seconds feels like a blink of an eye, but is long enough to cause severe injury. A fixed appliance, on the other hand, might allow a slightly longer disconnection time before serious injury occurs, as the user isn't directly interacting with it in the same way.
The standard provides detailed guidance on earth fault loop impedance, which, to simplify, is the total resistance of the entire fault path from the point of fault back to the source. And Table 8.1 contains calculated examples of the maximum values of earth fault loop impedance for various common circuit breakers and fuses based on these required disconnection times.
What's truly clever here is that if the calculated or measured earth fault loop impedance is found to be too high, meaning the protective device won't operate fast enough to meet those crucial disconnection times, the standard offers solutions. Supplementary equipotential bonding can be used to effectively reduce the impedance, or alternative protective devices like RCDs with lower operating currents can be employed. This demonstrates a flexible, problem-solving approach to achieving critical safety thresholds, providing different engineering paths to compliance when direct methods might be challenging or impractical. It's about ensuring safety no matter the configuration.
Special environments, tailored safety.
Okay, here's where we get into some truly fascinating specific scenarios. Water and electricity are, as we all know, a dangerous combination, and the standard reflects this with incredibly detailed special rules for wet areas. It meticulously classifies areas around water into zones: Zone 0, Zone 1, Zone 2, and Zone 3, each with precise dimensions and strict restrictions on what electrical equipment is permitted.
These zone classifications are incredibly precise, showing the foresight in risk management. Zone 0 is literally the interior of the bath, shower, or pool itself, where you are immersed in water. Zone 1 extends immediately above it, where you might be wet. Zone 2 reaches further out, where splashing is still likely. For example, a shower with a base but without barriers, as illustrated in figures 6.3 and 6.4 of the standard, has exact measurements defining where each zone begins and ends. A critical consideration then becomes why this granular approach, specifying every millimeter.
Seems very detailed.
Because the risk of electric shock changes dramatically with proximity to water and the likelihood of a person being wet or immersed, which significantly lowers the body's resistance. Every zone represents a different level of risk and therefore requires a different level of protection.
And the restrictions on equipment are incredibly strict within these zones. Socket outlets shall not be permitted in Zone 0. You won't find a power point in your bathtub, thankfully. In Zone 1, they're only permitted for very specific pool equipment. In Zone 2, luminaires and appliances are allowed only if they are self-PIL, extra low voltage, individually separated, Class 2 double insulated, or Class 1 with 30 mA RCD protection. This effectively bans ordinary household appliances from close proximity to water, which makes perfect intuitive sense.
It's all about minimizing risk where moisture is present. And this meticulous approach extends to decorative fountains and water features too. They have their own zones, requiring very high ingress protection, IPX8 in Zone 0 for immersion, IPX5 in Zone 1 for jets, and wiring systems for them must be suitable for immersion and protected from mechanical damage. Luminaires must be supplied by individual sources at very low voltages, typically a maximum of 12V alternating current or 30V ripple-free direct current. This highlights the extreme caution required around decorative water installations where people might interact with them, turning what seems like a simple aesthetic feature into a complex safety engineering problem.
Moving from wet to cold, refrigeration rooms and freezers also have quite specific rules.
Yeah.
The standard classifies the entire area within the refrigeration room as a single zone.
What's a striking deviation from general rules here is that protection by means of obstacles and protection by placing out of reach are not permitted methods of protection against electric shock in refrigeration rooms.
Really? Why not?
This is a critical departure because people often spend extended periods in these rooms for work, and those methods don't offer sufficient protection when someone is deliberately interacting with the space, often in confined areas. It also notes that standard PVC cables might not be suitable if subject to bending below 0 degrees C, referencing Table 3.2, as they can become brittle and crack. All wiring enclosures and cable entries to equipment must be sealed with a compound that does not set hard, where they pass from refrigerated to non-refrigerated spaces.
To stop moisture getting in.
Exactly. To prevent moisture retention and ice buildup, which can damage insulation and create conductive paths for faults. And here's a definitive ban. A switchboard shall not be installed in a refrigeration room. This is due to the specific environmental risks posed by the cold, condensation, and potential for moisture ingress affecting sensitive electrical components.
Similar to refrigeration rooms, areas subject to general hosing down operations for sanitization also have prohibited protection measures. Protection by means of obstacles and protection by placing out of reach are explicitly ruled out for similar reasons of prolonged human presence and increased risk from water.
And quite logically, electrical equipment in these zones shall be selected and installed to be suitable for the temperature and pressure of the fluids used in the hosing down or sanitization process. This ensures the equipment won't fail or be damaged during rigorous cleaning procedures that might involve high-pressure sprays or aggressive chemicals. It's about designing for the real-world operational environment.
Now let's consider safety services. Think about the critical systems that must function even when everything else fails. Emergency lighting, fire alarms, smoke venting systems, and even lifts in a fire. These have their own incredibly strict set of rules. The standard even updated their name to Safety Services, in line with international standards like IEC 60364.
The supply arrangement for these systems is absolutely fascinating and vital. Main switches for safety services shall be connected on the supply side of all general electrical installation main switches and not be subject to the control of any general electrical installation main switch.
So they stay on no matter what.
Precisely. This ensures they remain powered even if the main power to the rest of the building is cut off, which is absolutely essential in an emergency. Imagine a fire and the main power trips, but the emergency lights stay on, the fire alarms continue sounding, and smoke vents clear the air. That's the principle. These circuits also often need to maintain integrity under fire conditions. The standard refers to the WS classification system, AS&ZS 3013, which classifies wiring systems by their ability to maintain circuit integrity under fire conditions for a specified period and against mechanical damage. For instance, smoke venting equipment and lift circuits often require a WS52 rating, meaning they must operate for a minimum of 2 hours during a fire. This highlights the incredible robustness required for life safety systems, literally designed to function while a building burns around them.
Wow. From engine-driven generators supplying backup power to solar inverters feeding clean energy into our homes, electricity generation systems that connect to an installation have their own special requirements.
A critical safety point here, particularly for systems that can feed power back into the grid, is preventing what's known as backfeed. The standard demands that the generation system shall not impose a voltage on the installation at the network point of supply outside the limits specified by Clause 1.6.2c. This directly prevents dangerous backfeed into the main utility grid when the utility power itself is out. This is a severe risk to line workers who might be trying to repair downed power lines thinking they are de-energized.
Yeah, of course.
The standard even includes clear illustrations for generator supply interconnection, Figure 7.3, and solar supply, Figure 7.5, to clarify these crucial connections and safety mechanisms. It's about protecting the utility workers as much as the homeowner.
What about systems like SLV or separated extra low voltage and PLV or protected extra low voltage? These are designed to operate at very low voltages. Are they inherently safer?
Yes, their inherent design makes them much safer. These systems are specifically designed to provide protection against both direct and indirect contact simply by operating at very low voltages, typically below 50 VAC or 120 V DC. Sources of supply for these systems include safety isolating transformers, batteries, or motor generator sets with electrically separate windings. The broader implication here is that by minimizing the hazard inherent in the voltage itself, they become much safer to interact with, even with less robust insulation. And here's a surprising detail for these systems that you wouldn't expect for typical power outlets. Socket outlets for SLV and PLE systems shall not be provided with an earthing contact.
No earth pin.
And no earth pin. This distinct design feature helps to clearly distinguish them from standard outlets and, crucially, prevents hazardous connections to a conventional earthing system, which could inadvertently compromise the safety by separation these systems rely on. It's a very specific design choice for safety.
Finally, let's touch upon hazardous areas, places where flammable or combustible materials are present, and the stakes are incredibly high.
These are environments where even a tiny electrical spark, which would be completely harmless in a normal environment, could be an ignition source for a catastrophic explosion or fire. The standard is very clear and places a significant burden on The responsibility for classification of a hazardous area rests with the persons or parties in control of the installation. This means the owner or operator of the facility must engage experts to identify and classify these areas, then ensure strict adherence to specialized standards like ASNZS 60000790001 for gas vapor environments and ASNZS 6000079.10.2 for combustible dust. A critical consideration then becomes, why is this responsibility so critical and so highly specialized?
Because getting it wrong could be disastrous.
Exactly. It requires deep knowledge of the properties of flammable substances and how they interact with electrical equipment. The standard even includes an illustration of the hazardous area presented by an outdoor gas cylinder, figure 4.0, to help visualize these often invisible risks, highlighting that even seemingly innocuous everyday items can create a hazardous zone requiring special electrical precautions.
Verification and ongoing safety.
Okay, it's one thing to install everything meticulously according to the rules, but how do we truly know it's safe and will remain so? The standard places immense emphasis on verification, inspection, and testing. It mandates that all electrical installations and any alterations shall, prior to being placed in service or use, be inspected as far as practicable and tested to verify that the installation meets the requirements.
This is the crucial final step before energizing any new or altered installation. What's particularly insightful here is the explicit instruction. Precautions shall be taken to ensure the safety of persons and to avoid damage to property and the electrical installation equipment during inspection and testing. Obvious. This isn't just about the outcome of the test, but the process itself. It means the act of testing must be performed safely, ensuring that the electrician carrying out the tests and anyone else nearby isn't exposed to hazards, and that the equipment itself isn't damaged during the verification process. It's safety all the way down.
And it's certainly not a one-time thing. The standard emphasizes that periodic inspection and testing of electrical installations shall be performed in accordance with the requirements of 1. The regulatory authority, or 2. The owner or occupier of the premises. The standard specifically references ASNZS 3019 for recommended periodic testing arrangements, highlighting the absolutely ongoing nature of electrical safety. It's a continuous commitment, not a checkbox.
So what are some of the key specific tests performed to ensure compliance? One crucial test is insulation resistance. This test is vital to ensure that the insulation resistance between all live conductors and earth, or, as the case may be, all live parts in earth, is adequate to ensure the integrity of the insulation. It directly uncovers potential weaknesses in the insulation that could lead to electric shock hazards from inadvertent contact, fire hazards from short circuits, and equipment damage. It's also often performed between the conductors themselves for mains and submains to detect insulation breakdown between them. Think of it as a health check for the electrical skin of your wiring.
Another vital test, often referred to as ZEES, is the Earth Fault Loop Impedance Test. This test verifies the integrity of the N, or multiple earth neutral, connection and the upstream neutral conductors, and it directly measures the impedance for the complete circuit. This test needs the supply to be available, as it measures a dynamic characteristic of the live circuit.
It's essentially verifying that if a fault does occur, there's a low resistance path back to the source, ensuring the protected device will trip rapidly. If this impedance is too high, the fault current won't be sufficient to trip the breaker quickly enough, creating a dangerous situation. And finally, the operation of those crucial RCDs. Tests shall be performed on each final subcircuit protected by an RCD to verify that the RCD operates to disconnect the designated circuit. In Australia, this can be done either via the integral test device built into the RCD itself, the little test button, or by special test equipment that simulates a fault.
The push-button test.
Right. In New Zealand, the integral test device is sufficient if compliance documentation confirms its operation for both alternating current and pulsating direct current residual currents. This is a vital check on a key safety device, confirming it will indeed trip as designed when a dangerous leakage current occurs, potentially saving a life.
So what does this all mean for you, our listener? We've journeyed through the intricate and surprisingly detailed world of ASNZS 3000.207, from the overarching principles of electrical safety to the minute details of cable selection, equipment placement, and the highly specific rules tailored for environments ranging from swimming pools to refrigeration rooms. We've seen how these living documents are not static, but constantly updated to reflect scientific and technological progress, all with the singular goal of keeping us safe in an increasingly electrified world.
Yeah, if we connect this to the bigger picture, it's abundantly clear that the safety we often take for granted in our homes and workplaces isn't accidental. It's built on a foundation of meticulously crafted standards, painstakingly designed to protect you from direct contact, indirect faults, overcurrents, and a myriad of environmental hazards. This level of foresight and ongoing vigilance is truly remarkable. This raises an important question, though, doesn't it? In a world of rapidly evolving technology, from smart homes to electric vehicles, and with the rise of new power sources and more decentralized energy systems, well, how might these wiring rules adapt further? How do they integrate things like wireless charging, bidirectional power flow, and ever more complex energy landscapes while still upholding those fundamental, unchanging principles of safety?
It's certainly a thought to mull over, isn't it? The next time you flick a switch, plug in an appliance, or even just relax in your home, you'll know a bit more about the invisible, intricate blueprint that keeps the current flowing safely through your home and workplace. We hope this deep dive has given you some truly surprising facts and left you feeling much more well-informed.